Hi everyone, Mr. Boltri here, bringing you video 4.5. We're going to talk about the center of mass. So first we're going to define center of mass and then talk about how to calculate it. We're going to end the video talking about how this connects to what we've already learned in this unit, momentum. So first of all, what is center of mass? Center of mass is defined as the single point that represents the mass-weighted average position of all the mass in the object. So we'll talk about what this word means, mass-weighted, but let's think about just the average position of all the mass in the object. So if we take a baseball and we think about all of the mass in the object, some of it is over here and some of it is over here, some of it's in the top left and the top right, and we take all and we average all of those out, the average position of all the mass is going to be pretty much in the middle of the sphere of the baseball, which hopefully makes sense because this has a uniform density and is a pretty regular shape. But let's say that it didn't have a uniform density, and this is where the mass weighted idea comes in. Let's say that I actually made kind of a trick baseball, and then I hollowed out the bottom third, and I filled it, instead of whatever is inside a baseball, I replaced that with cement to make the bottom of it really heavy. So the mass weighted, the cement is going to have more mass, so it's going to lower the center of mass of the baseball, because we take all the mass that's up here, and then all the mass of the cement, which is denser, and therefore there's more mass. So then the average position of all the mass in the ball is going to be closer to that high concentration of mass at the bottom of the ball. So that's kind of the idea of center of mass. So let's do some examples. For example, let's again assume that this has a constant density, which might be an unfair assumption because the grass at the top might not be the same density as the dirt at the bottom, but let's just assume that it has a constant density. The center of mass is going to be in the middle. And then if the density changed, then it might move up or down based on that. And just to be clear, I'm going to be showing the examples of some 3D objects in 2 dimensions. So this dot at the center of mass is actually in the very middle of the cube. It's not like on the outside edge of a face or anything. It's going to look a little bit more like this, where this red dot represents the center of mass. The only thing that I would change about this visualization is I would take that red dot and I would squish it down to be way smaller, because the center of mass is represented by a single point, so which is a tiny thing. So this big red dot is a little bit too big to show the center of mass, but at least it shows that it's in the center of the cube. Okay, moving on to a little bit more of a complicated example. If we take this hollow frisbee, where's the center of mass of this? So some of the mass is up here and over here and over here and over here. And if we average it all out, turns out the center of mass is actually right here in the middle of the shape, which might be a little bit weird to you because the center of mass is not actually on the object anywhere. It's kind of like inside the object. And just so you know, that is totally okay for the center of mass to either be inside the object, in an actual space that exists inside the object, or just inside the space somewhere inside the object. So here are 2 examples of centers of mass, and these work for pretty regular shapes with uniform density. So as we saw in the cement example, or if we didn't treat this grass as the same as the dirt, changing the density changes where the center of mass is. It makes it a lot harder for us to figure out where the center of mass is. So we're actually going to do a center of mass example with an irregular shape. And then in our next video, we will do something with a non-uniform density. But if we just focus on irregular shapes, where's the center of mass of an object that's a shape like this? And more importantly, how do we figure that out? So in order to answer this question, I actually have to answer a different question first, which is, where's the center of mass of a system of particles? So here I have a system of 1, 2, 3 particles. Let's treat them all as one big system. And I want to know, where is the center of mass of this 3-particle system? So I need to know the mass of each particle and the exact location of each particle. Let's say we have something really heavy, 4 kilograms, 2 kilograms, and 1 kilogram. And then at different positions on my coordinate plane. So the question is, where is the center of mass of this object? Well, since this is the most massive element of the system, it's probably going to be close to this, but then this 1 kilogram is going to pull it down and pretty far to the right. And this 2 kilograms is going to pull it quite a bit down and then a little bit to the right. So the center of mass of the system is probably going to be somewhere in this region, but we can actually be much more specific than somewhere in this region by using this equation. So to find the x coordinate of the center of mass, what we're going to do is we're going to take the mass weighted average of all the x positions. So all this is doing is taking the x position of my first point and multiplying by the mass of my first point, and then the same thing for the second point and the third point. So then we're going to divide by the total amount of mass to find the mass weighted average of all the positions. So what this looks like in practice is the first point is 4 kilograms and has an x position of 1. So we're going to do 4 times 1 plus, then we'll do the same thing for the second point, 2 kilograms times an x position of 3, and then 1 kilogram times an x position of 5, and divided by the total mass is going to give me an x coordinate for the center of mass of around 2.14, which I'd say on the coordinate plane is about probably right here-ish. Which seems about right. It's closest to my 4 kilograms, but it's been pulled to the right a little bit by the 1 and the 2 kilogram. So what I ask that you do now is pause the video and do the same thing for the y coordinate of the center of mass by using the same equation and then just replacing all the x's with the y's. So if you do that, you should get a y coordinate for the center of mass of 1.57. Which is again the mass weighted average position of the center of the average of the masses. So then that looks like just kind of it's right here, which again makes sense because it's closest to the heaviest object, but it got pulled down and to the right. So that is how you find the center of mass of a system of particles, which isn't that fascinating of an exercise in itself, except insofar as it allows us to calculate the center of mass of an irregular shape, such as this one. So what we can do is we can do a very similar thing with our point particle center of mass calculation, except here we don't have point particles, but what we can do is we can break this into some regular shapes that we can know and understand. So some regular shapes would be this red rectangle and this blue rectangle, which might be kind of a square. And so then because now this is a regular shape, hopefully with a uniform density, then we can find the center of mass of each of these two shapes, which then we can treat those centers of mass as point particles. And then if we can calculate the density and therefore the mass of each of these two shapes, then we can calculate the mass weighted density or the mass weighted average of these two point particles, and then treat that as the center of mass of the whole thing, which would be right about here, which makes sense because this sort of box up top is going to pull the center of mass to be a little bit up and to the right of where it would have been if it was just this red rectangle. So that is how you calculate the center of mass for an irregular shape. And I'm not going to show all the math out right now because we have plenty of time to do some practice problems in class. So then it might be pretty reasonable for you to be wondering at this point, what does this have to do with what we've been talking about up until this point? Seems like it's coming completely out of nowhere, and I totally see where you're coming from. So I actually want to show you how this is connected to momentum in something that I think is really cool. So if we want to find the momentum of a system, it would be taking the mass times the velocity of all the individual elements of that system. But if we were only given information about the center of mass, then basically we'd have to take the mass weighted average. This should be M2, but we're fine with that. Hopefully I can convince you that this is the same as the momentum of the system is equal to the total mass of the system times the velocity of the center of mass. It's basically taking the mass weighted average of all of the velocities, which is basically taking looking at the velocity of how the center of mass of the object is moving. So this is a very powerful equation, and I want to show you two ways in which this equation is doing a lot of work. So one way is we've been looking at parabolas and things that are moving in parabolic motion. what we've actually been looking at is how the center of mass is moving through space. So if we throw this wrench, the center of mass of the wrench actually traces out a parabola, even though if we were to look at the tip of the wrench, it would be sort of flying all over the place, kind of making a zigzag through the air that wouldn't look very much at all like a parabola. But if we look at the center of mass, then that actually traces out a parabola through the air, a perfect parabola. So this is actually really important because the projectile problems that we've been doing up until this point have actually been kind of oversimplifications. We've been looking at the center of mass of the object without even really talking about that's what we've been doing. That's how powerful this equation is it's kind of been governing what we've been doing all along. We just kind of haven't talked about it up until this point. Another example is that if so we can look at this equation and then slap some deltas in there and say that, well, if all the forces are internal to the system, there's going to be no change in momentum of the system, which means that there's going to be no change in the center of mass, or there's going to be no change in the velocity of the center of mass of the system. So let's say that this system starts at rest, the system of the boat and the ball and the teacher. And if that system starts at rest, then it's going to experience no change in velocity, assuming no external force. So when the teacher pushes on the ball, that is an internal force, which is not going to cause a impulse. So therefore not going to cause a change in momentum, and therefore not going to cause a change in velocity, which is weird because the ball clearly moves to the left if the teacher were to push on it. And probably it would make sense for the teacher and the boat also to move to the right. So how is it that we can say that there's no change in velocity? And that is because if we look at the center of mass, the center of mass is not going to move. So as the ball is moving to the left, the teacher and the boat are moving to the right to make sure that the center of mass stays in the exact same place, which this is a really, really cool thing in itself. And it's also really important because AP loves to ask problems about this. They love to ask problems where the momentum of the system doesn't change. There's no impulse, no external forces. So therefore, and it's usually easiest if it's at rest. So therefore, the center of mass of the system has to stay in the exact same place. So then you have to calculate, well, if the ball is moving to the left, that is mass that is moving to the left. So then mass also has to move to the right to make sure that the center of mass stays in the exact same place, which cool and very important for the AP exam. So that's kind of a win-win combination for us. So we're going to do some practice problems applying all of the stuff we just talked about, calculating the center of mass, but especially applying that to the concept of momentum and explosions and collisions in our next class. But for now, this is Mr. Boltri wrapping up video 4.5, and go Bears.